Hi, this is our last lecture, which is dedicated to the calculation of the class group in large degree number fields. It's a part of the isogeny-based cryptography summer school of Bristol 2021. I put some lecture notes in a link to a lecture note in the comment section of this video. So let's recap with what are the main steps of the class group computation following the sub-exponential method. We have a factor base, so a base of prime ideals, the first n prime ideals. Those classes are assumed to generate the ideal class group, which means that we have a surjective morphism that takes a vector of n entries and map it to the power product of the pi corresponding to these powers. That is surjective, and so what it means is that the kernel of this map is giving us exactly the structure of the class group via the quotient of n z to the n by that kernel. So finding relations of the form product of the pi to the alpha I equals a certain alpha in k, that is the key to finding the class group, finding enough of them. And of course you need to compute this quotient, but computing this quotient is easy through polynomial time linear algebra methods. So it's really the finding of all these relations that is the bulk of the work here. The main ingredient in large degree is a reduction of ideals in order to take a random product and find a reduced element that lies in the same equivalence class in the class group. So how do we proceed? Well, we're assuming that we're given an ideal I, and then we take its inverse and write it down as C over L, and then we take a lattice reduction method of C. So typically we'll use BKZ if we want to find an asymptotically interesting result, and we'll use size k equals n to the 2/3, okay? So with that size, then we'll return whatever is the first reduced element in the basis divided by L. Now, what is the interesting property of that element is that so let's call that alpha, and when you multiply the input I by alpha, what you get is an ideal which satisfies two important properties. So first, of course, is it's in the same equivalence class of the original ideal I, but on top of that, its norm is bounded, okay? It's bounded by the invariance of the field, the degree, and the discriminant, so degree n and discriminant delta, in an interesting way, because what we want here is to ensure that it has good odds of being a product of the small primes that are in the factor basis, okay? So the smaller that ideal is going to be, the higher the odds that it could be broken down into a product of small primes, much like integers. If you draw integers at random, of course, the larger the integers, the less likely they are to be a product of small primes, okay? Same happens here. So the runtime of this procedure is essentially given to us by the runtime of BKZ with the block, so exponential in the size of the block. So you don't want that block to be too large, but the larger it would be, the better would be the bound here. So this is a compromise, okay? Now, how do we decompose an ideal? So assume you're given an ideal, you're going to multiply it by random product, okay, for small generators, small powers, that you hope take you uniformly at random anywhere in the class group. And then what you do here is whenever you end in the class of A times the product over I less than, say, a certain L0, so we don't want that many generators to appear here, wherever you end up in this class, you want to find an element in this class that has small norm by doing the BKZ reduction from the previous slide. And then what happens is, if that element happens to be smooth, so if it happens to be a product of the elements in the factor base, which again, the odds of that are essentially comparable to the odds of a given integer to be smooth with respect to a certain set of primes, okay? So choose your favorite set of the first I consecutive primes, and then draw numbers at random and see what your odds are at at having your numbers you draw being a product of those primes you selected at the beginning. And you'll see that this is essentially the odds of ending up in the situation. Every time the situation happens, what it means is you have your relation here. So you've rewritten in terms of ideal classes. You have the class of A, which is the class of a product of the pi with a certain vector here, yi minus xi, okay? The runtime of that, of course, is given to us by the cost of reduction and the odds of that happening. So however many times you need to repeat this. So this is chosen to be balanced. So the cost of reduction is about the number of times that you have to repeat this. Now, this is in the sense, this is the Hafner-Macaulay method, just generalized. But so if you input, in particular, if you input the trivial ideal, and what you do is you get this procedure gets you elements that are relations between your generators. So it's performing the task that we had before when we described in the previous lecture the Hafner-Macaulay class group algorithm for imaginary quadratic fields. So here we're talking about spitting out some relations between the generators of the class group. So the question is, could we say, well, could we argue that we have a proven runtime under the GIH? So here, unfortunately, as of now, we have to rely on a few heuristics that claim that essentially things happen just the same way as in the Hafner-Macaulay algorithm. So what are they? First, we need to say that we've landed uniformly at random in the classes when we did our reduction. Okay, so this is basically saying that the smoothness should be the same as the smoothness of integers. This is proven in the case of forms, of reduced quadratic forms, but this is conjectural when we're working in high degree. Okay, when the degree goes to infinity, that's where it becomes really hard to argue that we have a good distribution for the smoothness probability, to claim that it actually behaves like we were drawing random integers. Okay, and the other one is, of course, once we engage in this game of finding relations, is how random are the relations that we draw. In particular, when you get an x here, are you getting always the same x's, or are you getting x's that belong to the same sublattice? Well, you would want to argue that you hit different cosets with with a good enough probability and that is not necessarily the case unless you accept a second conjecture that basically tells us that we need the same number of iterations asymptotically as in Hafner-Macaulay to complete our lattice of relations. Okay? So we've briefly presented the sort of differences between classical computation when degree grows to infinity versus when the degree is fixed, where things essentially work the same as in the Hafner-Macaulay paper. Now, for the purpose of isogeny computations and the kind of problems that we have in isogeny-based cryptography, this was not directly relevant, but I figured that it would be interesting to have that as sort of like a showing how those problems can branch out to some open questions when the degree grows to infinity, because also this has connections to cryptography, but the lattice-based cryptography, not necessarily isogeny-based cryptography, but because these problems are connected, I thought it would be interesting to have that as a conclusion to the series of lecture. I thank you all for your attention, and I will be there for synchronous sessions on the week of July 5th to July 9th. Thank you very much.